Okay, welcome all. Today we have Dr. Dhagash Mehta here with us. He is with UTRC currently. So he has traveled around a lot in the world, various different countries, various different research labs, and he has gained a lot of rich experience from various good people. So he got his PhD in the Department of Applied Mathematics and Theoretical Physics. So he's an applied mathematician and theoretical physics person from the University of Cambridge in England. That was your master's, right? It was his master's. Then he went on to Australia, to University of Adelaide, to get his PhD. Then he went to University of Ireland, Syracuse University, again back to University of Cambridge. He did a lot of different postdocs at all these different places. And recently he was a research assistant professor at the University of Notre Dame in Indiana. And after that, he joined United Technologies Research Center. And currently his work focuses on optimization, machine learning, and applied mathematics. So today he is going to talk to us about the computational algebraic geometry methods. So, Dhagash,
thanks very much.
And sorry, before you start your talk, there are some mandatory instructions I need to give. There are 2 emergency exits there. There are bathrooms on these 2 sides. There are sign-in sheets, so please do fill in if you haven't. And there are some survey for the seminar, so fill out the survey before you. Okay, sorry.
Yeah, thanks very much. Thanks, Ashwin, for having me here, and thanks for your attendance. Even though this title sounds a bit abstract and too long, I still appreciate you attending this talk. Hopefully, the whole talk is not so abstract as a title. So I come from academia. Most of my life has been spent in academic research. It's the first time ever where I'm at an industrial lab. Okay? So I used to plan out my research projects in terms of seasons. So in next spring, next fall, and next autumn in the British system. Now I have my schedules planned in terms of weeks. Okay, that's the change I'm trying to adjust. But it is still a research center. I don't know how familiar you are with United Technologies. It has all these subsidiaries, ODEs, elevators, carrier air conditioners, Pratt & Whitney, and United Technologies Aerospace, and many small companies, which even I cannot enumerate right now. But United Technologies Research Center, which is situated or headquartered in East Hartford, where we develop and do research for all these industrial segments. So we still do quite mathematical, slightly more abstract research, and also engineering research. I am an applied mathematician or theoretical physicist by training, okay, but I still find my good place here at UTRC in many research areas. And this research, the topic of this research is based on research that I did previously before joining UTRC, but I'm hoping to continue with this research, okay, at UTRC as well. And I'm just in East Hartford, so this is our office. So you can always email me, and I can always come back here. Okay, I just live here in Connecticut. So I'm going to talk about some novel computational techniques that I developed along with my collaborators, and I applied these techniques to some real-life problems, especially in synchronization. And then I'll also briefly mention about some electrical grid or power flow equations. Okay. And I don't assume any prior knowledge on algebraic geometry or anything here. Okay, so just sit back and enjoy the talk. So there is this place in Tennessee, Gatlinburg. It's in the Smoky Mountain area. And there is a specific species of fireflies which just happen to be there along the whole US mountains. This species can be found just here in Gatlinburg. So as the evening begins, fireflies, of course, fire. They start firing randomly. Okay? After a few minutes, they start firing in synchronized fashion. Okay? So all the fireflies will fire in synchronized fashion. There's synchronization observed in some biological systems. It's a beautiful scene there, and the Gatlinburg City Council also organized shows for the synchronized fireflies. They just collect money. The show is, of course, run by the fireflies. So, but that's one of the synchronization phenomena that you can observe in biology in real life, but you can also observe this kind of synchronization in audiences. I was at Notre Dame before coming here, and always in game nights we have this rhythmic applause, and people immediately start clapping in rhythmic fashion. You can also see synchronization in power grids and electrical networks. Also, neural networks are also known to have synchronization. So there are many other places where you can also see this kind of synchronization. And the most popular model to study synchronization is called the Kuramoto model. Kuramoto was a Japanese mathematical physicist, and he came up with this elegant-looking model. It's an ODE system. Okay, so d theta I for dt is equal to some nonlinear function. Okay, so I'll explain each term individually. So theta i's are the frequencies or the phases of each firefly. Okay, that's a phase with which the ith firefly fires. Okay? And omega I is their normal frequency. So if a firefly does not know what other fireflies are doing, then this is the frequency with which it will fire. So if it is isolated, then this is the firefly's frequency. That's called normal frequency. But they just don't fire individually. They also know what other firefly is doing. So that's this coupling term. And here, this coupling means that there is a sinusoidal knowledge among the fireflies. Here I'm assuming that the whole network of fireflies is a complete network, which means that each firefly knows what everyone else is doing. Okay. You can also come up with your own network, like random network, or just nearest neighbor network. So each firefly knows what its nearest neighbors are doing. Or you can also come up with some cyclic graphs and small world and so on. Okay? All the graph theory you know. And here, this coupling strength, K, is basically the strength of knowledge among these fireflies. So here I'm assuming that the amount of knowledge is equal. Okay? So each pair of fireflies knows what other pair knows. Okay? You can also think of putting more complexities such as Kij here instead of just K. So then you can control this coupling strength for each pad individually. Okay. Here I'm just for simplicity assuming that Kij, all Kij is equal to K. Okay. So that's the model, and it is a system of ordinary differential equations. And in this model, you can start from K is equal to 0. Okay? When each firefly is just isolated entity and it's firing with its own phase. In that case, they do not synchronize. Okay? Obviously, they don't know what others are doing. Then you start increasing K from 0 to some small number, say 0.1. Then there is no synchronization. Then you put 0.2 and so on. Okay? So you keep increasing K from 0 to some finite number. At one particular point in K, they all will synchronize. Okay? So that's the spatial value that we are interested in. Okay? Yeah?
Is it obvious why there should be a single unique solution to this K? To the theta that where they have the same value?
No, and that's the whole point of this talk. There is no single solution. If you are asking if there is single stable state here, then for the complete graph, I observed that yes, there is only one stable state. But there are still many unstable states. But that is not obvious. So this particular spatial value of K that we are after, it's called critical coupling. So beyond Kc, this system will always synchronize. Okay. And below Kc, it will not synchronize. Okay. So something happens exactly at Kc. Okay. So Kc is called the critical coupling, and many exact results for Kc are available for n tends to infinity limit. The results come from statistical physics, where n tends to infinity, infinitely many particles is well-studied system, and you can apply all those results here in this system, and you can come up with analytical closed form formula for Kc. Okay? But n is infinity here. So, which is usually not realistic. There are always finitely many oscillators, finitely many neurons, finitely many nodes in your or generators in your power grid, and so on. Okay. So you ultimately have to know something about finite n. And for finite n, the crude most way to find out this Kc is exactly what you might have thought of. Start from K is equal to 0, take some initial condition, and solve this ODE, okay, with MATLAB, for example, with your preferred ODE solver. Then put K is equal to 0.1, again solve the dynamical system with given initial condition. See if this fireflies synchronize or not. Go back, K is equal to 0.2, and so on. Okay? At some point, you will see synchronization. So you go back and do this bisection or K, and you hope to find critical coupling in that sense, okay? In that way. But there are several problems with this crude procedure. So first, any ODE solver is obviously dependent on initial condition. Okay? So if you find some strange initial condition, you might never converge. Okay? And it always happens to many other systems. What if there are multiple stable state states? Okay? So because this is a system of ordinary differential equations, once you solve this ODE, it will go to some attractor, okay? Some stable state. What if there are multiple stable states? Okay? In ODE solvers, there is no way of knowing if you have multiple stable steady states or not.
Right.
Yeah.
So what does it mean by no synchronization when k is below kc?
So in terms of equations, you mean d theta I over dt minus d theta I minus 1 over dt is equal to 0. So the difference between frequencies is 0.
So when that value is below the critical point, it never goes to one synchronization state.
Yes.
Just
Yeah,
so
yeah.
is it possible to have like a 0, 1, 0, 1, like a half of them?
Yes. So
Fire.
that is called clustered synchronization, which is also another phenomenon. You cannot see it in this particular model, but you have to add some more terms, and you can see clustered synchronization. Some of the oscillators are synchronized, some of them are not, and they are called chimera states, arriving from Greek mythology, chimera. So one is lion and the body is horse and something like that. But you cannot see it directly in this particular formulation of the model. So I'm just talking about pure synchronization. So either you have all synchronized or not, okay, or none. So that's and the third point is that ODE solver is also dependent on step size. Yes, and that's technical detail that you have to care for. And what if there is no stable steady state? What happens to your ODE solver if there is no stable steady state? It will just keep on computing your trajectory, but it will never converge to one particular attractor. But you don't know if this ODE solver did not convert because there was no stable steady state, or it was just a bad initial condition. There is no way of knowing it here. So this crude procedure might not work that well, okay, especially if you are after some rigorous results. So before going for my procedure and my strategy, I just want to mention that finding this critical coupling for this particular model basically reduces to finding steady states of these equations. So essentially solve these equated to 0. Okay? That's equivalent to say that difference between frequencies is 0. Okay? So if d theta I or dt minus theta I minus 1 or dt is equal to 0, you can show that this is equivalent to that condition. Okay? So essentially, we have to solve these equations for each value of k. Okay? Now, what is the benefit of viewing this problem in terms of solving equations rather than solving these nonlinear equations rather than ODEs? So here, so I was doing my PhD back in Australia, and I was trying to solve these equations. And after a long, frustrating year, I realized that I could put sine theta I as SI, okay, and cos theta I as CI. So of course, you have to assume that I have expanded this. So instead of sine x minus y, I write sine x cos y minus sine y cos x. And then I put sine theta I as SI, cos theta I as CI. Okay, that brings me here, these equations. Now this is not clever. It's just reformulation of the same problem. I would just call sine theta as S and cos theta as C. Nothing unusual. But then I put these equations, the additional equations, which tells you that the same trigonometric identity, sine squared theta plus cos squared theta minus 1 is equal to 0. And I put this for each and every angle. Okay. So I have now bigger system to solve. So this is my original system in terms of S and C. And these are n additional constraint equations, which just tells these equations that your C and S are just sine and cosine. Okay? But I have increased my system. So instead of n equations, I now have n equations. Okay? So what's the benefit here? Now, instead of trigonometric equations, I have polynomial equations. Okay? So I have transformed my problem set into a problem in algebraic geometry. Okay? So algebraic geometry is nothing but theory of polynomials in the crude description. So anything related to polynomial equations is essentially algebraic geometry. So why algebraic geometry? So the equations have to be algebraic. You cannot have log and exponentials and all. Okay? So you have to have polynomials or algebraic equations. And it also deals with the geometry of the solutions of these equations. Okay? So there is this interplay between algebraic equations and their solutions. That's why it is called algebraic geometry. Okay? That's all we need to know for now. Once you have algebraic geometry problem, once you have system of polynomial equations, there are some sophisticated computational techniques that you can apply to solve these kind of equations more efficiently. Okay. So, yeah.
Is there an active sign?
Yeah, it should be.
Where?
Omega I minus that should be 0, right?
Oh, here, yeah.
Also, because the system is quadratic, does it mean it will be convex?
So these, if you had a cost function quadratic, then it would be a convex function. But here, the equations themselves are quadratic, so it can have multiple solutions. So once you have system of polynomial equations, you can go to some novel computational techniques, and the two of them are the most important ones. One is called Gröbner basis technique, and the second one is called numerical algebraic geometry. Okay. And I always take some simple example to explain these methods. So forget about this Kuramoto model, sine and cosine equations. We just want to solve this system of equations. Okay? So it has 3 variables, 3 equations, and they are nonlinear. X and y are x, y, and z are all mixed. So I'm sure you can solve this equation, this system by hand. But let's pretend that you do not know how to solve this by hand. Okay? And you are looking for some numerical or computational method to solve this. Okay? So you go to either the Gröbner-based technique or numerical algebraic geometry method, and first the Gröbner-based. Okay? So here, very roughly speaking, once you have a system of polynomial equations, such as our running example, x, y, and z, you can transform this system to a new system of equations in the same variables, and this new system is easier to solve. Okay? And also another important point is that the solutions of your original system is always the same as the new system. Okay? So there is always exactly one-to-one correspondence. Either you solve the original system or you solve the new system. The solutions are the same. Okay? So you obviously solve the new and easier system. Okay? So that's the whole point here. You systematically transform your system of equations to an easier one. And the algorithm to do this is called the Buchberger algorithm, and the new system is called the Gröbner basis. So Buchberger and Gröbner both were Austrian mathematicians or computational scientists, and Gröbner was a student of Buchberger. Buchberger was a student of Gröbner, and he this new system after his advisor. And you don't have to write your own code if you don't want to. There are several freely available packages like Singular, Cocoa, Macaulay 2. Macaulay 2 is a Cornell University product, and Singular is a German university product, and Cocoa is from Italy. Magma is from University of Sydney in Australia. It is a commercial software, so you have to pay it until 2015. In 2016 or so, Jim Simons Foundation, Simons from the Renaissance Technologies, he bought the American license for Magma. Okay. So as long as you are in the US, you can download it for free. Okay. So Maple and Mathematica also have Gröbner basis implementations. So again, go back to our running example. So just to remind you, this was our system, X, Y, and Z. And I asked Mathematica to give me a Gröbner basis for that system, and it gave me this. Okay. So I told you that my new system, Gröbner basis, would be easier to solve than the original one. But it still has 3 equations and 3 variables. Okay. It's still nonlinear. What have I gained here? So if you look at it more carefully, the first equation is univariate, just one variable. Second one has 2, out of which one has already appeared. And the third one has the last remaining variable. So you solve this equation by hand here, because it's just univariate equation QB. Then you back substitute your 3 solutions here in this equation and solve for y. And then you back substitute x here and solve for z. Okay. So this new system is easier in this sense. So this system has 3 solutions, 1 real and 2 complex. So as you can see, I'm now also talking about complex solutions, even though my original problem might require only real solutions. I have expanded my solution space. So I collect all the solutions and then throw away all the complex solutions with imaginary part being non-zero, and retain only the purely real solutions. Okay. Here I'm not using any numerics here. Okay. There is no numerics. It's symbolic method, so it can be considered as exactly solved system using computer. So even mathematicians would be fine with this if you solve this using Gröbner basis technique. So that was the Gröbner basis technique, which is a symbolic method, and it guarantees you to find all complex solutions, hence all real solutions. And now the second method. Again, you are given a system of polynomial equations as this one. So I'll just written this in vectorial form. It's just our original running example. So in this new method, it's a numerical method. There are 3 steps to solve any system of polynomial equations. In the first step, you estimate at least an upper bound on the number of solutions. Okay. So what is the crude most upper bound on the number of solutions of any given polynomial system? It is called the Bézout bound, which is nothing but the product of degree of each polynomial. Okay. So here there are 3 polynomials, and the degree of a polynomial is basically the highest degree. Okay. So in this case, this has the highest degree. The degree of this term is 2. Okay. The second polynomial has degree 2, x squared. That's the highest degree. Here, this is also 2. So 2 to the power 3 is the maximum number of complex solutions this system of polynomial equations can have. That's the upper bound. That's a Bézout bound. And of course, there are many tighter upper bounds available in the market these days. So in the first step, you estimate an upper bound. Okay? In the second step, you construct a new system of polynomial equations in the same variables, say x, y, and z in our case, which follows these two properties. First, this new system has to be easy to solve. Okay? And second, it must have exactly the same number of complex solutions as this upper bound that you came up with in the first step. Okay? So here you came up with 8 number of complex solutions as the upper bound. Then this system also has 8 complex solutions. X, y, and z all plus or minus 1. So all combination of plus or minus 1. So 8 solutions here. And it is obviously easy to solve. Okay. In the third step, you combine this original system and the new system in one equation or one system. Okay. So this is your original system, this is your new system, and you put a parameter t so that they both are connected, okay, in one, using one parameter. So when t is equal to 0, this term vanishes and only your original equation survives. When t is equal to 1, this term vanishes and only your new system survives. Okay? And so now your strategy is as follows. You start with one of the solutions of this system and put t is equal to 1 so that this term vanishes. You just have this system. Take one of the solutions of this system and keep increasing or keep decreasing t from 1 to 0. Okay? So you try to reach from here to here. Okay? So again, take t is equal to 1 so that this term vanishes and only this term survives, for which you know all the solutions because that's how you constructed it. Okay. And you take one of the solutions and then keep decreasing t from 1 to 0 and try to see if you reach here. Okay. So this tracking can be done using any character predictor method. Okay. So, and this is called homotopy continuation method. I guess electrical engineers and many engineers are very familiar with homotopy continuation. This is homotopy continuation, except that I can now also track complex solutions here. Okay, so that's difference. I also include complex solutions. So now you might be wondering what this guy is doing here. So as long as you take some generic value for gamma, it is proven that no path from here to here will have bad behavior. Okay. For example, they won't turn back from G to F while going from G to F. No path will turn back and go back to G. Okay? That's not what you want, obviously. And as long as you choose generic value here, so by generic I colloquially mean random. Okay? Just random value here. Another thing won't happen is crossing two paths. No two paths will cross each other. Or there won't be any singularity along the path, and so on. Essentially, as long as you put some random value here, it is rigorously proven that no bad thing will happen. It will either go to this system or it will diverge to infinity. These are the only two possibilities. Okay? And this is a cartoon to show what I mean. So you start your 8 solutions at t is equal to 1 from here, from your new system, and then start tracking one by one. So for example, this path just diverged to infinity along the way. this as well, this as well. This path reached f of x. So you found a solution. Then this and this path also converged. So you found 2 more solutions. And then again, rest of the paths diverged to infinity. So now with this, the so-called gamma trick, again, it is guaranteed that you will always find all complex solutions with this method. It is a numerical method, but sharply different than Newton-Raphson or many other methods. Here, you are guaranteed to find all complex solutions of a system of polynomial equations. So that's a unique method in that sense. And again, there are well-written packages available for free. Bertini is a University of Notre Dame product where I was employed. Home for PS2 is the University of Illinois, Michigan State University product. PHCPAC is University of Illinois Chicago product. Okay. So before I go on describing my results for the Kuramoto model, I just want to show some differences between these two methods. So first, the Gröbner-based technique is a symbolic method. So it guarantees to find all solutions, okay, in most cases, except that I know some exceptions. For example, if you have your first polynomial equation, which is always a univariate equation, but if it is of degree 5 or more, then a classic theorem in algebraic geometry, it's called Abel-Ruffini theorem, which says that you cannot solve the univariate equation with degree 5 or more exactly in terms of its radicals, the radicals of its coefficients. You can solve ax squared plus bx plus c is equal to 0 exactly. You can also solve cubic and quintic equations exactly. But you cannot do it for beyond that. Other than some special cases like x to the power 5 minus 1 is equal to 0. You can solve that obviously, but not in general. Okay. So if you have your first equation in the Gröbner-based technique of degree 5 or more, then you are back to some numerical math. Okay. But you cannot always solve any given system of equations exactly. Here it is numerical method. It does not claim to give you exact results anyway. Okay? But it guarantees to find all solutions. So if you start with, say, some objective function in optimization, then you can take its first derivatives and solve these equations using this numerical algebraic geometry method. Then you can guarantee to find the global minimum, for example, or all local minima, all saddle points, and so on. Okay, so that's quite unique here. There is also a computational complexity issue here. It is the Gröbner-based or the Buchberger algorithm is known to have exponential space complexity, which means that if you add one more equation, then or one more variable and so on, then the RAM required by your machine blows up exponentially. Here there is no such major scaling problem. Of course, a bigger system will take more time and so on, but not exponential. So I also with this second point, I also get questions sometimes. That if you have some system of equations which is known to be exactly non-solvable, can I still solve it using Gröbner-based technique? No. Where will I see the problem while running this Gröbner-based computation if I have some exactly non-solvable problem? So say you give me an exactly non-solvable problem, I put it in my computer for Gröbner-based technique. It will take more time than the lifetime of the universe to solve that system. Okay? That's how you see that it is an exactly non-solvable system. And that's basically exponential space complexity hits you. That's my simple-minded definition of exactly non-solvable or exponential space complexity. The Buchberger algorithm is highly sequential. So each step requires knowledge of all the previous steps, which means that you cannot put it on a parallel computer. This method is called embarrassingly parallelizable. Each solution path can be tracked independent of each other. So if you have a big cluster, you can solve big system. There is some technical problem with non-integer coefficients here, and floating point coefficients are also one. So here, I don't usually call it a method, I call it a framework. In the sense that you can play with many things. Once you know your system very well, you can do many things. For example, you can come up with tighter upper bounds on the number of complex solutions for your system. Yeah.
I have two questions. First one is there any upper bound on the running time of this homotopy continuation method?
So there is no rigorous proof for this, but people believe that it is cubic.
Right. And the second question is, what are some similar other techniques like this one for solving system of polynomial equations?
So for solving nonlinear equations, there are many, but a method that guarantees to find all solutions.
Yes.
So one is the Gröbner-based technique. The only other method I know is this interval arithmetic, which is basically bound and branch. So if you give some bounds for all the variables, then it can guarantee to find solution in that particular bound. But then again, computational complexity is a major issue there. And if you don't have any solution in that bound, then it will just keep on searching. So probably the only practical method may be this one. If you have really large system, I would just go for this. And you can play around with your system. For example, if you know symmetries in your system, and power systems and many other engineering systems come with many symmetries and sparsity and so on. Okay. So you can come up with tighter and tighter upper bounds so that you have to track only fewer number of paths here rather than the Bezier number of paths. So that's why I call it a framework. You have a framework, but you can also play around with it and tune it for your particular system. However, I should be fair to this method. So we were working on this Sudoku problem. Sudoku, the Japanese puzzle. There are 9 by 9 blocks, and you are supposed to put integers from 1 to 9 in a particular way. And you can formulate this whole problem as a system of polynomial equations. So there are 81 variables corresponding to 81 blocks, and then you put some constraints so that you can satisfy all these rules of Sudoku. Okay. And the Gröbner-based technique finished its computation in just 2 minutes, and numerical algebraic geometry method just kept on tracking all the paths. It was mainly because the system itself came in very nice form. And there are lots of symmetries, and Gröbner is just computed it very quickly. So sometimes it works very well, even for a large system. Okay, so now go back to our Kuramoto model. Okay, that's where we started. These are our system of equations. And again, with this minus sign here, that's a typo. But so these are my results, and this work was with Florian Dorfler and Jonathan Hohnstein. John is at Notre Dame. Florian is now at ETH Zurich. Noah is now an assistant professor at Worcester State University. So here I'm plotting n, the number of fireflies, number of oscillators on the x-axis. Here I'm plotting Kc for corresponding n. Yeah. So Kc is the critical coupling for particular n. And these are some lower and upper bounds in the literature. And these are our results from our numerical method. And we have much better results now. Okay. So, but this part was much more surprising. So here I'm plotting K, the coupling strength, and here I'm plotting the number of equilibria, number of steady states, not just stable steady states, all steady states, okay, all equilibria. And as you increase K, number of equilibria just blows up. It goes all the way up to 10 to the power 5. Okay? Just for 18, n is equal to 18, I have 10 to the power 5 number of steady states. So the phase space of this ODE system is quite rich. And we also saw some conjectures in the literature. For example, if there was a stable equilibrium for a complete graph, then the difference would be less than pi over 2. And we disproved it by counterexample. Okay? With these numerical methods, we found all solutions, and then we did not find any such solution. So it was disproved by counterexample. And many other results for complete graph and for other graphs as well, like cyclic and Adolf-Steiner random graphs. And we are also trying to go further with eigenvalue analysis, and also we want to include stochastic versions. So not just a Kuramoto model, but Kuramoto model plus some stochastic variable, some random variable. And I also worked on the power flow equations. So these are power flow equations in a particular formulation. And there are many formulations of the power flow equations. Okay. So this is one of them. And apparently the power flow equations are just algebraic equations. They are polynomial equations. That was quite fascinating. It is one of the systems where algebraic geometry naturally arises. I know only one more such example. In particle physics, algebraic geometry naturally arises. So there is this debate in particle physics whether God is algebraic geometry or not. Okay? Because at the fundamental level, you can explain everything in terms of polynomial equations. And that's the basis of string theory. Okay. But don't want to digress. So these are power flow equations, and again, I exploited symmetries of these equations, and then found all solutions for example, up to n is equal to 14 bus cases for the IEEE test systems. And this work was with Konstantin Turistin at MIT and his student Hung Nguyen. So this was the first paper where someone found all equilibria of these power systems. And I'm also working with Aranya Chakraborty at North Carolina State University and his student on multi-stability in wind energy systems, and also exploiting sparsity of the power flow equations, and so on. So I'm working on several other things as well, and I might not go explaining everything here, but for example, dynamical systems on graphs. It's a big area, and I can find steady states of dynamical systems on networks. Okay, so that's my specialty. An optimal power flow problem. That's also always one of the most interesting problems in power grids. And you can also apply these techniques to machine learning, belief propagation, and computer vision, and so on. So that's where I stop. Any questions?
Thank you, speaker. Any time for questions?
Is there a physical meaning for the K factor? In the case of the fireflies.
In case of the fireflies, so fireflies is a special system where you cannot control the amount of knowledge that is transferred. But if you consider, for example, power grids, then you can control many things so that you can control the overall coupling strength among the generators. And you can tune it so that it is synchronized or desynchronized as you like. That's
my question is more, is there any biological mechanism that we understand that regulates or controls that K?
So that's what I'm saying. So in fireflies, you cannot control anything. They are just doing their own stuff. You are not going to be able to control anything. But for example, in neural networks, you can inject some drugs to control the coupling strength, and basically it's medicine.
But I think they have shown that Kuramoto model works for the fireflies.
Yeah.
So
Do they measure the K or?
Yeah. So what is how do
I don't think
measure
they
K
measure
for-
K. They just assume that K is such that they are synchronized. So K is in the synchronization region, but they don't know the exact value of K, exact value of Kc.
So maybe two different groups of fireflies might synchronize with two different values of K.
Yes.
Well, since there is no unique K for which they're synchronized, then how do you know
That's
that
true,
you're
yeah.
just not tweaking the value of K?
Yes, so in the case of fireflies, it will be almost impossible to formulate this problem so that you can measure K. But in power networks, for example, you can do this. You can come up with some voltage, combination of voltage and those things to which will mimic K.
This threshold behavior, so is it particular to the synchronization problem, or is it an artifact of this kind of model? That by threshold I mean there is a critical value for K under which no synchronization and over there is synchronization at this one. So this behavior.
I think it is particular to this model. You can always come up with some model which always synchronizes.
So what kind of models do show this kind of threshold behavior?
Power networks. So so I think these equations are precisely power flow equations in a special condition. So if you fix some of the impedance matrix elements to 0, then you will recover these equations precisely, exactly. So power flow equations in a very specific case. So I think it's called lossless networks.
To follow up on that question, are there any competitive models to Kuramoto?
I think there are many others. This is more popular mainly because it is very elegant and simple to state.
Okay.
So for the analytic way of solving those system of nonlinear equations, Do you mean that you are making a coordinate transformation? So you choose a different set of basis vectors where the...
Yes, exactly. So it is. So if you have a system of linear equations, then to solve this, you will do Gaussian elimination, and you will bring it in the upper triangular form.
Yeah, that's what it looks
exactly
like.
what
Yeah,
it is.
yeah.
It is a generalization of Gaussian elimination
For nonlinear.
for nonlinear. It is exactly that.
So I saw that in the third equation was not in 3 variables. So is that typically how you get it, or?
I think the first equation. So the number of variables increases as you go down, but there is no specific rule.
Okay. So it need not be always a triangular matrix. Well, it is, but okay. All the entries may not be non-zero. Okay. Any other questions? All right. Let's thank the speaker. Yeah.